first question was, why does air hold 20 times more oxygen than cold water? And why warm water holds less dissolved oxygen than cold water? In this homework, the person correctly pointed out in air, 210 mils of oxygen per liter, 790 mils of nitrogen, and a small amount of carbon dioxide. So here's water. One problem is water has trouble entering. There are more molecules in the way in water than air, so it's easier for an air molecule to leave than come in, because it may collide with the water and head back out. More importantly is the hydrophobic effect. And oxygen on this water is hydrogen bound to a hydrogen on another water. So these oxygens and hydrogens are hydrogen bonding. What happens is the water molecules keep trying to get close to each other, and the hydrophobic effect pushes oxygen away, tending to push it out of the water. So it's the low affinity. Now, not part of the question, but why does water hold so much more carbon dioxide than oxygen? Here the issue is, even though carbon dioxide is a nonpolar molecule, it still has uneven distribution of charge. These oxygens are a little bit negative. They're more electronegative than carbon, and so the carbon's a bit positive. And so carbon dioxide actually will hydrogen bond with water molecules, whereas oxygen won't. In an oxygen, that the two oxygens are equally electronegative. They share their electrons equally, so they are completely neutral. Why does temperature matter? Well, with more random molecular motion, these water molecules are jostling more to get next to each other, pushing the oxygen out even faster. Here is another way of saying it. This one was a little bit simpler. Water molecules are attracted to each other, but not oxygen, so oxygen is pushed out. There's our oxygen not being attracted and tending to push out. So at equilibrium, there's 20 times as more oxygen per liter in air than there is in cold water. And as the water gets hotter, that additional random molecular motion just pushes the oxygen out even faster. And at boiling, at 100 degrees centigrade, all of the oxygen gets carried out, gets pushed out. So I wanted you to think about the movement and path length of oxygen from the air to a cell in the brain. And you want to separate out the distances over which diffusion occurs and the approximate diffusion distances versus bulk flow. Bulk flow doesn't depend upon diffusion. And so that's the only reason we can be as big as we are, because we can use bulk flow to push oxygen around to different parts of the body. So the diffusion takes place between the air in our lungs across a thin epithelial layer with basement membrane. And this is correct, that epithelial layer with basement membrane to the capillary, that is going to be less than 0.5 millimeters. And in fact, in a human, that distance is much less than that. The basement membrane is typically about 100 nanometers, only 0.1 microns. And the epithelial layer is often about the same. And same with the capillary. So this whole distance can be as low as about 200 nanometers, or 0.2 microns, or 0.0002 millimeters. So much less than this. It would be more like this distance for this whole thing. So that gets oxygen by diffusion across a short distance into a capillary. Then by bulk flow, blood pressure being created by the heart, pushed around through the heart into a capillary in the brain. And again, less than 100 microns. So typical cell is no more than about 5 cell diameters from a capillary. And so on the order of 100 microns, maybe a bit more, as the furthest oxygen has to diffuse to get to a cell. So we have path lengths that may be well under a micron, and about 100 microns here. What about a mucus layer? So if we get excess mucus here, well, that simply increases the path length. And the path length where you're absorbing the oxygen is pretty critical. And so even a 5 or 10% increase in thickness here due to mucus is going to cause about a 5 or 10% slowdown of oxygen. And so less oxygen in the blood, and it's more difficult to get oxygen into the blood and to the rest of the body. In this question, I wanted you thinking about a real problem, which is particulate matter 2.5 microns. So these are particles that are under the size of a cell, but not that much under. And a problem here is that these particles generated by air pollution, they're not removed in the mucus. They're a little bit too small to be easily moved in mucus often. Instead, they get taken into cells. Essentially, they're treated as if they might be a bacterium. Notice these are about the size of a bacterium. An E. coli is about 3 microns by 1 micron. And so they're attacked as if they are a bacterium or a potential parasite. So what happens is these particles get in, they get trapped in the mucus, and macrophages that may move into the alveoli absorb these, and the scale is about right here. If this is about 20 microns, here would be a particle. They get absorbed, but they can't be digested. A bacterium or other organic material can often be digested. These cannot, and they can build up in a cell. In some cases, they can puncture. Some of them are sharp, and they can puncture them. Anyway, they kill the cell, and they release contents of the cell, damage-associated molecular patterns, or other signaling molecules, so DAMPs. Those bind to receptors, so we've got some kind of signal, could be a hormone or some other message. More likely not a hormone going to the whole body, but a molecule that's a paracrine signaling molecule. In other words, goes to nearby cells. So here is a fibroblast. That fibroblast would be somewhere nearby here. And that fibroblast starts to secrete collagen. Okay, makes vesicles of collagen, fuses those with the membrane, and then the collagen starts to self-assemble into this thick scar tissue. And now we have thickened scar tissue, and we've got a greater path length. Anywhere that you've got that collagen there, you're blocking it. In fact, it might even be tight enough that oxygen can't easily get through it. Certainly it increases the path length and slows it down. Here was another way of showing it. Here's the alveolus. Here are these particles. They're getting into the lung. Here's a macrophage picking them up. That macrophage, so here is a macrophage. That macrophage dies. It triggers a fibroblast to start secreting collagen. So here's the fibroblast, and here's the collagen it's putting in. So it's replacing damaged cells, or it's just putting in collagen at some location here, and that is going to slow down oxygen movement into the cell. Fourth was to show a normal fish gill showing countercurrent exchange, and then what would happen if you reversed it. So let's start with this one. Here are the lamellae of a fish, and the water is moving here across them, or between them, coming out here, between them, coming out here, and 100% water, 100% oxygen, saturated with oxygen coming in, and it's encountering deoxygenated blood that's going through the lamellae like so. So with countercurrent exchange, we have the water going this way, starts at 100% here, and it's always encountering blood that's coming in the other direction from an area where there's less oxygen, and so this person decided this was 90%, and we get net movement, and so this would leave at above 90% actually, maybe 95. Here, 20% of the oxygen is gone, but it's encountering blood that has even less, and so again we have oxygen moving. So oxygen keeps moving from our source to our sink, and we can get, if this keeps on going long enough, we can get to the oxygen in the water being nearly depleted, whereas but still passing oxygen to the blood, and so on. So what would happen if you reversed it? Well, if you reversed it, they're both going the same direction. And so this person started with 30% partly oxygenated blood. Here's the water at 100%. We definitely have oxygen shifting here from 80 to 50, so we're moving 20% out, 20% into here. Now 15, 15, and now it'll just stay at 65% as long as you go. We've exchanged to the point where they're equal, and now instead of having near 100% saturated with oxygen, we've only got 65. Another one showing basically the same thing. Here's the normal setup with 0% and 98% in the lamella. Here's the water at 100% and down to 2%. We've removed almost all the oxygen into the blood. Reverse the direction. Now we have the deoxygenated blood going the same direction as the water. We're at 100% in our source, 0% in our sink. We're going to wind up with 50% in the blood and 50% in the water.